Hello and welcome to today's lesson looking at direct and alternating potential difference. This lesson is suitable for students carrying out the GCSE, AQA separate and combined sciences for physics looking at the electricity topic. So in today's lesson we're going to look at what alternating and direct current is, and you are trying to look at understanding how alternating and direct current operates. So if we are successful and we learn in today's lesson, we should be able to define and describe alternating current, define and describe direct current, and then find electrical values from oscilloscope traces. So it falls into the following part of the AQA separate science and combined science specifications for physics. So in the electricity topic, we're going to be looking at 4.2.3.1, which is direct and alternating potential difference. So in previous lessons, we've considered the concept of electrical current. But what do we mean by electrical current? So what is it? What causes electrical current to flow? How do you calculate current? And what is current measured in? So electrical current is a flow of electrical charge. The size of your current is the rate of flow of charge in the circuit. And then again, the electrical current flows when the potential difference is put across a conductor in a complete circuit. So it's fair to say that a potential difference causes an electrical current in a conductor. We know that current can be calculated with the equation current is equal to charge in coulombs divided by time in seconds, and then finally current can be measured in the units amperes or amps. So when electrons move in the same direction to cause a flow of charge, a current is produced in the conductor, but this can be produced in two different forms. So what are the two different types of current and how do they link to each other? Well, there's two types of current. The first type of current is what we call direct current, or DC. Now, direct current occurs when the charge, which is normally free electrons, it is free electrons in all metals, when they all flow in one direction only. So in this example, the free electrons would move from the negative part of the battery to the positive part of the battery. Now we find that direct current occurs in batteries. So in cells and batteries supply a direct potential difference, which then produces a current which always flows in the same direction, which is what we call direct current. Now, alternating current is when the charge, most likely free electrons, moves backwards and forwards in the conductor to generate a current. Now, the posh name for moving backwards or forwards is to oscillate. So we say that the charge oscillates in the conductor. Now, the mains supply, which is what you plug your devices into, it produces an alternating potential difference given an alternating current. Now, the frequency of the mains, how often it changes, is 50 Hertz. So there are 50 cycles every single second. So an alternating current, charge flows one way and then the other way in successive cycles. So you can see in this particular example, an alternating current is one where the charge are constantly changing direction. Now the mains electrical supply is AC, and in the UK it has a frequency of 50 cycles per second, or 50 Hertz. Hertz just means the number of cycles per second. So it means that the charge will change direction and move back again 50 times every single second. So we can summarize direct and alternating current with the following picture. So direct current is found in batteries and it's movement in one direction around a circuit. Now alternating current is found in the mains and there's no overall movement because the charge oscillates backwards and forwards about a point in the circuit. So let's just clarify that again. There are two types of current, the rate of flow of charge, which can move through a conductor. The first type is direct current. Here, all the electrons follow the same direction in the conductor, so there's a direct current going through the conductor. A direct current is produced in a conductor by direct potential difference, and the potential difference is placed across the conductor, which is normally provided by a battery or a cell. Now, the second type of current is an alternating current. Here, the electrons all oscillate in the same formation in the conductor, so the electrons move backwards and forwards in a conductor. So there's no overall displacement by the charge, so that we say there's an alternating current through the conductor, and an alternating current is produced in the conductor by an alternating potential difference, and we place this alternating potential difference across the conductor, which is provided by the mains normally. Now, in alternating current, we tend to find that the positive and negative terminals of an alternating power supply swap over with a regular frequency. So for the mains, like we said before, that's 50 Hz. Now, measuring devices such as voltmeters and ammeters are typically used in circuits to measure current and potential difference, but these struggle to actually measure alternating current and alternating potential difference. They tend to be used to measure direct current and direct potential difference. So many experiments carried out in a school classroom tend to use direct current and direct potential difference. But if you wanted to measure alternating current and alternating potential difference, you've got to use another device. So the device we use to measure alternating potential differences and alternating current is called an oscilloscope. Now these devices can actually show both alternating and direct supplies, but these ones can especially good at showing alternating supplies. Now an oscilloscope is a device used to illustrate and display energy. So an oscilloscope displays the energy in a system, and it can be used to measure many different types of energy. And the full name of an oscilloscope is a cathode ray oscilloscope. So to display the alternating potential difference of an alternating current easily, the oscilloscope, which is basically an advanced voltmeter, is used to display the potential difference. So what we do is the many oscilloscopes are connected to a signal generator. These are devices that can easily generate an alternating potential difference. And the trace can then be observed on the oscilloscope, which is made by an electron beam moving across the screen. And we can use the oscilloscope screen to determine the key values about the alternating potential difference. Now the display of an oscilloscope looks like the following. The y-axis represents the potential difference of the circuit, and the scale of the y-axis is called the y-gain. So for example, if we set the y-gain to 2 volts, this means every vertical square on this scale represents 2 volts. And the y-gain can be altered by an investigator in any experiment. So here's a picture of a y-gain on an oscilloscope, and you can see it can be 0.2, 0.5, 1, 2, 5, 10, 20 and 50. So what we tend to do is to improve the accuracy of any results that we take, the y-gain should be set so the entire waveform can be displayed on the y-axis. Now just to note, negative values on these axes represent the alternating nature of potential difference in current, i.e. it means when the charge is moving the opposite direction to when it started in. So if the line of the oscilloscope trace stays either solely positive or negative, it can be considered a direct supply because the charge is only moving in one direction. Now the x-axis represents the time of the measurement. Now the scale of the x-axis is called the x-gain. Now for example, if we set the x-gain to 20 milliseconds, that means every horizontal square on the oscilloscope represents 20 milliseconds. Now again, the x-gain can be altered by the investigator in any experiment. So here we can alter it to 100 milliseconds, 10 milliseconds, 1 millisecond, 100 microseconds, 10 microseconds, 1 microsecond. So again, to improve the accuracy of the results, the x-gain should be set so the entire wave can be displayed on the x-axis. Now an oscilloscope can actually have its time base turned off as well. This means the x-axis no longer represents the time and the waveform is not considered a wave that changes with respect to time. It just shows the potential difference. So this means the wave would only be represented by the y-axis of the screen. So if, for example, we turn the time base off, you would only see a dot if there was direct potential difference. So it would look like this on your oscilloscope screen if we turn the time base off and it was a direct potential difference. But if it would produce a line if it was an alternating potential difference. So if we turn the time base off, we would achieve the following result on our oscilloscope screen for alternating potential difference. So we can show the different types of current and potential difference with an oscilloscope. So in this example, the oscilloscope will be set where the potential difference is on the y-axis and the time is on the x-axis. So this produces an image of how the potential difference and the current vary in an electrical circuit. So here's an example of an oscilloscope trace. So the pulse across the screen will represent the energy. So this is an oscilloscope trace for an alternating current and alternating potential difference. Now, the highest value possible is what we call the peak voltage, which for the mains we will consider to be 230 volts. volts. So you can see here the following. So in the main supply, the peak voltage is 230 volts. Now it actually varies from plus 230 to minus 230. Now why does it vary from plus to minus? It's because the charge, the electrons, are moving in opposite directions. Now the pattern produced on your oscilloscope trace is called a sine wave. So you can see that the positive values indicate the charge or the electrons are moving in one direction, and the negative values indicate the charge or the electrons are moving in the opposite direction. They're going backwards and forwards. Now potential different readings should be taken from the center point of the wave of the oscilloscope trace, which is what we call the equilibrium position. So we actually say that anything away from equilibrium is called the displacement from the 0 point. Now we can use the alternating potential difference trace to work out the frequency of the alternating current. Now the frequency is the number of waves of alternating potential difference in 1 second. So how you work it out is as follows. You work out the time period of one wave, which is the time taken for one complete wave to be observed on the oscilloscope. That's when the charge goes in one direction, then the other direction, and back to where it starts again. So it goes negative, then positive, then back to 0 again. Now we can then work out the frequency, because frequency is equal to 1 divided by the time period. So there's our time measured, our time period, and then we can measure our frequency in hertz and our time period in seconds and say frequency is equal to 1 over the time period. Now you're actually given this equation in your examination. You're not expected to memorize it, you're only expected to use it. Now the frequency of the mains potential difference is 50 hertz. That means in the mains, the alternating current has electrons, charge, moving backwards and forwards 50 times every single second. So that actually implies to us, by the way, that if the frequency is 50, the time period must be 0.02 seconds, because 1 over 0.02 seconds equals 50. Now, this is the oscilloscope trace for direct current. Now, a flat line indicates a direct potential difference in a direct current, because the charge is only moving in one direction. It's only staying positive or it's only staying negative. Now, the larger the supply, the higher the line. So a direct current is produced by a direct potential difference. So we can use the scale of the oscilloscope trace, the Y gain, to work out the potential difference of the direct source. So if, for example, we said that the Y gain was 2 volts, we look in this particular example and it's 2.5 squares up, so therefore each square is 2 volts, so that means the direct potential difference in this trace is 5 volts. So let's just summarize what we've learned. Alternating potential difference is shown as the following on an oscilloscope screen. The frequency of alternating potential difference in hertz is equal to 1 over the time period in seconds, and a direct potential difference is shown as the following on an oscilloscope screen. Now let's just note something. Placing a diode into a circuit can change alternating current or potential difference into a direct current. Now the reason why this is because a diode only allows charge to flow in one direction, regardless of the type of potential difference. So if you put a diode into an alternating potential difference circuit, it would turn that alternating current that the potential difference produces into a direct current, because it only lets the charge flow in one direction, either positive or negative. So it would remove either the negative values of your oscilloscope trace or your positive ones, depending on the orientation of the diode. Now this process of changing an alternating current into a direct current is called rectification. So we say that it rectifies alternating to direct current. So what have we learned in today's lesson? We should know that the mains electricity is an AC supply, and in the United Kingdom the domestic electrical supply has a frequency of 50 Hz and is about 230 volts. Now you should be able to explain the difference between direct and alternating potential difference. So if we've been successful and we've learned in today's lesson, we can define and describe alternating current, we can define and describe direct current, and we can find electrical values from oscilloscope traces. I hope you've enjoyed today's lesson on alternating and direct current, and have a lovely day.